Okay, so we are looking at part C and question number A. So convert the instructions to machine code and fill in the content of working register, file registers and status registers. There's a note here. All the 5 instructions are dependent of each other. And here we can see a memory map of data memory, which is starting from hex 200 until hex 300. So the content of those file registers are given here, so which will be used for the question. So here we can see the initial condition is given, move LB hex 3, which means we are activating bank 3, which is this instruction here. So this is activating bank 3, and this is the machine code for that, and the initial content of working register is hex 5. All the other content of file registers is assumed to be 0, and the status register has the following initial condition. So let us look at the first instruction. This is LFSR, so load the literal value into FSR, and we're choosing FSR 0 and we're loading the value hex 200. So the first thing we need to do is we need to find out what is the machine code for this instruction. So we can refer that to the instruction set. Where is that? Not this one. Yes, as you can see here, let me just select that, and this is the LFSR. So this is the machine code for it, as you can see. So what we'll do is we'll write it back here. So we'll just take the space below here for the first one. So for LFSR, let me just get the machine code for LFSR would be, as we have seen just now, is 1110 1110 00 FF, and then you can have the KKK. This is a 32-bit instruction, so the second 16-bit is 1111. It's all 4 zeros and followed by K. So the instruction format looks like this: LFSR, F and K. So why am I writing like this? So that you can relate with the question. The question writes LFSR FSR 0 and hex 200. So as you can see here, the F refers to the FSR, which FSR that you choose. So for PIC18 we have FSR 0, FSR 1 and FSR 2. So we have 3 FSR that we can choose from. So therefore there's only 2 bits here which will allow us to choose from either one of these FSR. If we are choosing FSR 0, the value of this 2F will be 0 0. If we choose FSR 1, this will be 0 1. If we choose FSR 2, this will be 1 0. So that's how the values is going to be. And here you can see KKKK. This is 12 bits literal value. This 12 bit, which is this one, this is 12 bits literal value of the address that we want to point. So I don't have much space here, so I'm just going to write like that. So basically we need to fill in, this is already given to us, this LFSR, FSR 0 and hex 200, which means we need to load this value so that the LFSR 0 will point to this address. So now we need to substitute the value. So 1110 1110 00. Now the FF, because we're choosing FSR 0, so we're going to write as 0 and 0. And what about this? As you can see here there is 12-bit address. This is first 4-bit, 4-bit and 4-bit. So how the arrangement is, let's say assuming that this is the first nibble, this is the second nibble, and this is the third nibble. So this 4 bit here will represent the first nibble, this will be the second, and this will be the third. That's how the arrangement goes. So if that's the case, so what should be the value for this KKK here? We're referring to the first nibble, or what we call as the most significant nibble. So the value would be 2, so it would be 0 0 1 0. And the bottom one, this is the same, 1 1 1 1 0 0 0 0. The remaining the second nibble and also the third nibble is also 0, so we're going to write it as 0 0 0 0 0 0 0 0. So we don't leave the answers in binary, so we need to convert them to hex. So this one, the top 16 bit will be hex. What is this? This is E. The second one is E. Now this is 0 and this is 2. The bottom one will be hex F0 0 0. So this is the answer for the first one. So we write here hex E 02 hex F0 0 0. Now when we execute this instruction, does it affect the working register? Let me just bring this down back so that you can see. Does it affect the working register? No, it doesn't affect the working register. So what will be the content of working register? It will remain the same. And of course this is not related. And does this instruction affect the status register? How can we find that? We can look that at the instruction set. This is LFSR. If you look here at the status affected, it is mentioned none, which means the instruction doesn't affect status register. So in that case, the content of the status register remain the same. Let us go to the next one. Add the content of working register to the file register. Now if you notice here we are using indirect addressing mode plus W0. So we have to know where is this location pointed to. So as we have learned in class, so this is for the first one. Let's do for the line here. Let's do for the second one. So what is the instruction there? It is add the content of working register to file register, which is being pointed by plus W0, and you store the answer back in working register. Now when we see this instruction, this is something like this. We have the content of working register and you plus with the content of a file register. This will be the file register, but the file register is being pointed by this plus W0. So what does plus W0 means? It means that the new address pointed is equals to the content of FSR 0. How do I know that this is FSR 0? Because you can see here is plus W0 plus with the content of working register. So what is the content of FSR 0? If you remember, we have just loaded it with 200. So the content of FSR 0 will be 200 plus with the content of working register. So what is the content of working register? The content of working register is 5. So here will be hex 05. So what will be the total? The result will be hex 205, which means this address is the address being pointed by the plus W0. So here we can actually replace this with the value hex 205. Now let us try to do the addition now. Let us try to do the addition. So what is the content of the working register? earlier we have seen it is hex 05. So that we know, hex 05. And what is the content of 205? 205, we have to refer to this memory map. So you can see address 200 is here, 205 is this one. So the content of 205 is hex 06. So I'm going to write here hex 06. So when you perform this addition, what is the answer that you get? You will get hex, this is 5 plus 6 is 11, so it is hex 0b. And where do you store this? You are storing this back into working register. So for this indirect addressing mode, there is no machine code, but then you have to fill in the content of working register. The content of working register is the answer, because the destination is working register. So you have to load hex 0b into working register. So the value into working register will be hex 0b. The file register, this is not related. So status register, how do we know whether the instruction affects status register or not? We can look at the instructions here. As you can see, addwf, the status affected is all the 5 status bits is affected. So we have to check the answer one by one to find out what is the final answer. So the answer is hex 0b. So based on the answer, we need to determine the status register. So 0b, is it negative? No, it's not a negative answer. Do we have overflow? So how do we supposed to know whether we have overflow or not? Is by looking at the sign of the numbers. Now the first two numbers which we are adding is positive, and the second is also positive. How do I know that? Just by looking at this number, it is 0. 0, this number here, this first digit, if it's 0 until 7 in hexadecimal, it means that the most significant bit is 0 and it indicates positive number. If it's 8 and until F, it means that the most significant bit is 1, and therefore it indicates negative number. So this is a positive number plus with positive number, and the answer you are also getting positive, which means the sign convention is correct. So there is no overflow. Is the answer 0? Now this is quite clear, it's not 0, so this will be 0. Do we have digit carry? Digit carry means in the first lower nibble, if you add and you have a carry here, this is known as digit carry. Do we have digit carry? No, we don't have digit carry, so it will be 0. Do we have carry? Carry means from the upper nibble you add and you have, it gives a carry, so we don't have carry as well. So the answer will be 0. Now let's look at the next one. Next is move the content of working register to the file register. So you're moving from working register to file register. You need to find out what is the machine code for move WF. Let me just put a line here so we can indicate this the next one. So we're gonna refer to move WF because we need to find out what is the machine code. So move WF, where is it? Okay, here. This is move WF, and it has the machine code of 0110 111A and then 8 bits of F. What is the question? Move WF hex 20A. So this is move the content of working register into hex 20, and this is the hex 20 is in working, is in access bank. So what is the machine code for this move WF? It is actually 0110 A F F F F F F F. So this is the F field and this is the A. So we need to fill in the A and also the F. So this is quite straightforward. So we'll have 0010111 A. Because this is access bank, the value of A, if it's access bank, is 0. If it's bank, it will become 1. And this 8-bit file register address refers to this hex 20. So you know, one hex digit is equivalent to 4 binary bits. So this one will give 4 bits and this one will give 4 bits. So the first one is 2, so 0010. Second one is 0, you get 0000. And we need to convert this into hex. So this is 6 and this is E and 20. So this is the answer for the machine code. So let us write here hex 6E20. Now what this instruction is doing, it is actually moving the data from working register to the file register. So which means you have working register and you have file register. This is working register and the file register is hex 20, and the value inside this working register was what is the value inside working register? It's 0B. It is hex 0B, and if you're moving it to another register, you'll also have hex 0B. So remember, the principle is always copy and paste. So what will be the content of working register? It still remains the same, hex 0B, because you always have this principle of copy and paste. What will be the content of hex 20? We have just seen this now. It will be hex 0B, because you're moving the content of working register to hex 20. Now does this instruction affect the status register? Let's find out. This is move WF and none, so which means it doesn't affect the status register, so the answer remains the same. Let us look at the next one. This is move from file register to file register. So as you can see here again we are seeing the indirect addressing mode is being used. Here we have an address which is already defined here, so we need to find out what is this new address. So let me just draw another line. So again we have seen that this is how we find the new address of which is being pointed. So we're going to do the same thing now. So what is the content of FSR0 plus with the content of working register? So what is the content of FSR? It has not changed. It is still hex 200. We have not changed it. Remember the previous plus W0 here doesn't change the value of FSR0. So which means FSR0 still remains at hex 200 plus working register. Now the content of working register has changed, so the value now is 0B. So will be hex 0B. So the new address is, which is being pointed, is 20B. So which means if we were to rewrite back the question, it is actually referring to like this: move FF hex 20B to hex 207. Is it correct? Is it 207? Yes, it's 207. So what is the content of 20B? We need to look here. 20B is A7. So A7 we are going to move to 207. So the value will be hex A7. What will be the value content of working register? It will be the same, because this instruction doesn't change the content of working register. Does move FF affect the status register? Let's find out. Move FF, none, so it doesn't affect. So it will remain the same, 0 0 0 0 0. And the last one is subtract working register from file register. Now is given an address here, but you are using banked. So which bank is currently active? Is bank 3. So which means the actual address is referring to is 303. So you need to subtract working register from 303 and you store back the answer in the file register. Now first and foremost we need to find out what is the machine code for this. So let me just draw another line. So we are doing on subtract working register from file register. This has F, D and A. And what is the machine code for this? Let me just find out. Okay, so the machine code is 010111 DA F F F F F F F F. So our question is subtract working register from file register, hex 03, store the answer, and it is banked. So this is the F, and this is D, and this is A. So we need to fill in the blanks. I mean, we need to substitute the values of D, A, and F. So it will be 010111. Because the D is F, you will get the value of 1. If it is working register, the value of D will be 0 because the file register will be 1. And A, because it's banked, the value of A will be 1. Let me just use a different color scheme for this. So this is 1 because it's file register, and it's 1 because it's banked. And 8-bit file register address is referring to 03, so 0000, and 3 is 0011. So how do we write this in hex? So this will be, this is 5, this is F, and this is 0 and 3. So this is the machine code for this instruction. So we're going to write here hex 5F03. And so let's go back here. So this is this looks something like this. This is actually subtract working register from file register. So the file register should be on top, so this 303, and this is supposed to be working register. So what is the content of 303? Let's look back here. 303 is 6E. It is hex 6E. What is the content of working register? We know that it still is 0B. So now we can perform the subtraction. E is actually 14. So 14 minus B is 11. So the answer is 3. And then 6, this one is minus 0 is 6. So this we get the answer 63. Well, where do we store this? We store it in back to file register, which means we store it back into hex 303. So let us try to fill in this one. What is the content of working register? It remain unchanged because we stored the answer in 303. So what is the answer here? It will be hex 63. Does this instruction affects the status register? Let us look. Subtract working register file register. Yes, it affects all the status register. So based on the answer, which is 63, we can find out the values here. So is 63 negative? No, it's not a negative number. It's not a negative number because it's 6. 6 means the most significant bit is 0. Do we have overflow? Now let's check it out. So this is a positive minus positive. You are getting positive, which is correct. This is a larger positive number. subtracting with the smaller positive number, you get back positive, so there is no overflow because the sign convention is correct. Is it 0? Definitely it's not 0. Now we need to determine the digit carry and carry, but because we're doing subtraction, it's going to be digit borrow and borrow. So did we have a digit borrow? Digit borrow means we are borrowing from the most from the upper nibble. This is digit borrow, and borrow means we are borrowing for the upper nibble. So we neither have digit borrow nor borrow. So what should be the value for digit borrow and borrow? Because the polarity is reversed, if there is no digit borrow, we're going to write 1. This is in contrast with addition. In addition, if we have digit carry, then only we write 1. Now because we're doing subtraction, if there is no digit carry, we're going to write 1. So it's in reverse polarity. And likewise, do you have borrow? We don't have borrow, so we're going to write 1. So this is the answer for this part. So this is still part C, question number B. So convert the following content in program memory into instruction sequence. So given here, this is the content of program memory. So what is our first sub question is decode the machine codes into instruction mnemonics. So in order for us to do this, the first thing we need to do is we need to extract the machine codes from the program memory. So how do we do that? So first and foremost, we know that one single instruction actually is 16 bits long, which means it will take 2 locations in program memory. So because this is an 8-bit microprocessor, and therefore the program memory can only store 8-bit at one location. So since the instruction machine code or the instruction mnemonics are 16 bits long, we need 2 locations in program memory to store one instructions. So the first thing we do is we actually divide the program memory in groups of 2s so that we can extract the instructions. So here we divide into 2 and then the second 2. So this will be the first instruction, this will be the second, and this will be the third. Now if you notice that the address is increasing as it is going down, so the smaller address is here and it is increasing as the numbers goes down. If you all remember that PIC18 is actually using little Indian method, which means the lower byte will be stored at the lower address and the higher byte will be stored at the higher address. So when we want to extract the information, so you have to make sure that the higher address is, the higher byte is stored at higher address, so write that 0E, and then the lower byte it will be stored in lower address, so we get 0E32. so this is the first instruction. Same thing goes with the second one. The higher byte is stored at higher address, so it's 6E. The lower byte is stored at lower address, so 1 1. And same goes with this one, 0F and 1 1. So now we have extracted 3 instructions or machine codes. So the next thing we need to do in order for us to decode the codes into instruction mnemonics is that from the hex we need to expand it to binary. Why? Is because in the instruction set we can see that the machine codes, the 16-bit instruction word, the machine codes are in binary. So if we want to find what is the mnemonics, so we have to expand the hex into binary. So let's take the first instruction, which is 0E32. So when you expand this, you will get 0 0 0 0. E is 1 1 1 0. 3 is 0 0 0, sorry, that is 0 0 1 1, and 2 is 0 0 1 0. So this is the first one. So how do we search for this? How do we search that? How do we search this machine code in the PIC18 instruction set? Is you can look nibble by nibble. You can search for which instruction has this first higher nibble first. So we can go to the instruction set. You can look, do we have any the higher nibble which is all 0. I'm searching here, we have all 0. But what is the subsequent nibble? The subsequent nibble is actually 1 1 1 0. So even though here we managed to find 1 is 0, but subsequent nibble is not 1 1, so that this is not the right one. So we go on searching. Yes, we found another 0 0 0 0, but the next nibble is not 1 1 1 0, so it can't be this one. Go, keep on going. So nope, nothing's here. Go to the next one. Definitely it's not going to be control instructions. So let's look at literal. Okay, we found it. So we have several upper nibble which are all zeros, but what was the subsequent nibble? It is actually 1 1 1 0. So you will notice that there won't be any duplicate instruction word. Every instruction word is unique. So this is 0 0 0 1 1 1 0, which is exactly matches our first two nibbles. So which means this instruction is actually belongs to move LW. That's what it shows here. So and the remaining 8 bits K is actually the literal value. So which means that this is actually the value K. So what is the first instruction? It is actually move LW, move literal value to working register, hex 32, which you get from here, the 3 and 2. How about the second code? This is hex 6E11. As the same method, 6 we need to convert into binary, is 1110. 11 is 0001 0001. So same thing, we look for the upper nibble first for 0110, and the subsequent one just is actually 1110. So let's go back to the instruction set. 0110 is not here, so we have to go back to the earlier table. Can we see 0110? Okay, 0110 is here, but the subsequent one is supposed to be 111, so this one doesn't match. We found another one, but the subsequent nibble doesn't match. Same with this one, same with this one. Let's go further down. Okay, we found 0110, and we have 111 AFFFFF. So which means this is the instruction that we are looking for. Where is it? Okay, 0110 111A. So can we find any other 0110 with 111? No, you see, there is 110, but it's not 111. So nope, you can't find. So which means this is the answer. Sorry, where is it? So this is the instruction that we're looking for. So this is move WF, F and A. So which means this instruction, the opcode is only up till here. This is actually A, and this is F. So this is move working register to file register. It has two fields, F and A. So the F field will be hex 11, and because the value of A here is 0, so it means that we are using access bank. So this is the instruction. This is a mnemonic for this machine code. The last one is hex 0f11. Same thing here, we expand it to binary. This is f, this is 0001 0001. So we need to look for the upper nibble which starts with 0. So let's go back to the machine code. Do we have all zeros? Yes, we have 1. What is the subsequent nibble? Is 1111. So the subsequent nibble is 1111. So we have all zeros, but this doesn't match. So this is not the answer. We have to look back, all 0. Okay, we found another one, but the subsequent one is supposed to be 1111. So this is not it as well. No, it's not here. So definitely it's not in the control operation. So here 0000. Okay, and then the subsequent nibble also matches 11111. Can we find any others similar like that? No, there's 0 here, but this doesn't match. 0 here, this one doesn't match. 0 here, the subsequent nibble doesn't match. Same thing goes with all this. So which means it belongs to this mnemonic, which is add literal to working register K. So this one is add literal value to working register K. So which means this is K, so you're gonna add with hex 11. So this is how we extract the 3 instructions. So the next one is what is the final value inside the following registers: working register and file register, after you have executed all these instructions. So let's use the visual aid. So let us draw so that we know what is actually happening. So we have working register and we have file register address 11. So let's go through each one of these instructions. The first instruction is move literal value hex 32 into working register. So you are loading hex 32 into working register. What is the next instruction? You move the content of working register to file register, which is at hex 11. So which means you're moving it, because copy and paste. So inside hex 11 you also have hex 32, and then you add literal value to working register hex 11. So which means you are going to add the content of working register with hex 11, and then you store back the answer in working register. So the final answer in the working register will be hex 43. This answer will be stored here. So what is the final value inside the following registers? Working register, the answer is hex 43. And what's inside file address hex 11? It is hex 32.